So we'll start with this chapter then. This is the last chapter, atomic physics. So at the beginning of these chapters, you can see radioactivity. Okay, so radioactivity means the atom which is not stable, so they emit some radioisotopes or maybe some ray. So because of that, we have radioactivities. And detections of radiations. So to detect the radiation, we need to use some instrument. So we want to understand that. So that's why at the first point, you can see background radiations. Background radiation is the radiations from the natural surrounding. Okay, from the natural surrounding. So even imagine our natural surroundings like stones or maybe some let's say trees, so they may have a very small amount of radiations. Okay, so that is what we call background radiation, and it's a small amount of radiations around us all time because of radioactive materials in the environment. Okay, so if you learn biology, you should heard of even in organisms, they should have some small amount of carbon-13, which is radioactive. So because of that, we have some background radiation. It mainly comes from natural sources such as soil, rocks, air, building, materials, food and drink, and even space. So all these give a small radiations. Okay, so what are we going to study here is a particular substance that release alpha, beta, and gamma. So that will be radiations, which is from that particular substance. For example, uranium. We use uranium to make radio decay happens, and then alpha, beta, and gamma come out. So the radiations will be much more greater in value compared to the background radiations. Okay, so because of that, we need to detect the presence of radiations by using an instrument, Geiger-Müller tube. So this is the tube. As you can see, the pictures is down here. Geiger-Müller tube is used to detect radiations. Okay, so you see here, the first point, the window is thin enough. The window is here, the orange color part, thin mica window. Okay, the window is thin enough for alpha particles to pass through. So alpha particle can pass through, beta can, gamma also can. So they all can pass through the Geiger-Müller tube. If an alpha particle enters the tube, it ionizes the gas inside. Okay, so this one we take it like this. Alpha particles is actually helium 2 plus. Is helium atom, I mean helium ions, helium that loses the electrons. Okay, so it become alpha particles. So when it comes to the surrounding with air, so the air molecule is affected by helium 2 plus. So basically what happens is the air molecules will break down into ions. Okay, imagine that's the helium 2 plus can't wait to take the electrons from the molecules. So because of that, the air molecule become ions. So it ionizes the gas inside. This set off a high voltage spark across the gas and a pulse of current in the circuit. So imagine, you can look at the pictures. You can see plus and minus in the tube here. Okay, so basically because of the alpha particles that ionizes the air molecule, so that's why there are positive ion and negatively charged particles inside. So because of that, the negative charged particle is moved to the wire in the middle, and then it starts to flow, and that creates current. Okay, current. So you can see spark also. So spark is something like the movement of electron to the middle. So that causes spark. The beta particles of gamma radiations has the same effect. It has the same effect. So we have alpha, beta, and gamma. Beta, gamma has the same effect, just that the ionizing power is not as much as alpha. Alpha has the highest ionizing power. Okay? So beta is moderate, gamma is the lowest in ionizing. Okay, so it can be connected to a rate meter. So this is the rate meter, and you can see the reading here 62. 62 means counts per second. 62 counts per second. Okay, so that means imagine one spark is taken as one pulse, one count. Okay, so in 1 second there are 62 sparks, and because of that there are 62 counts over here in 1 second. Okay, so you connect it to a rate meter or a scalar, which tells total number of particles or bursts of gamma radiations. So rate meter tell us count per second, but scalar tell us total number of particles or bursts of gamma radiations. So they tell us different things, but no need to know in details. So you just need to remember Geiger-Müller counter, Geiger-Müller tube is used to detect radiations. Okay, so now let's see characteristics of the three kinds of emissions. So we have radioactive emissions, occurs randomly over space and time. Occurs randomly, yeah. So that means if you have a piece of uranium is a very famous atom, which is used to produce produce nuclear energy. Okay, so it's a very famous one. So it has emission, radioactive emissions, which is alpha, beta, and gamma, come up from uranium. So it occurs at any time, and it occurs randomly. Not affected by the surrounding. So that is what they're trying to say. So the emissions of that radioisotopes releases alpha, beta, or gamma. So alpha, beta are particles, but gamma is energy. So you see the nature here. Alpha is helium nucleus. Helium nucleus means heliums without electrons. So helium, if you remember that, helium is actually He with 4 and 2. 4 is the nuclear number, 2 is the proton number. So that means there are 2 protons, 2 neutrons, and 2 electrons. So now the alpha particles is helium-2 plus. So what happens is it still have 2 protons, 2 neutrons, but no electrons. Okay, so that is called alpha particles, so helium nucleus. The charge is positive 2. The penetration is kind of weak. You can stop it by using a piece of paper. As you know, the size is kind of big compared to the other two. So this is a big size. So that's why a piece of paper can stop it. Effect from field, deflected. Effect from field means what happens if you put it in an electric field, what happens if you put it in a magnetic field. So it's deflected. Okay, deflected. So why is deflected? Because they have charge, it's positive charge. If you put it in electric field, it will deflect to the negative terminal. Okay, so if you put it in magnetic field, of course, you have to follow a certain direction based on Fleming left-hand rule. Okay, we'll discuss that when necessary. Ionizing effect, very strong. That's what we discussed just now. The A molecule will change into ions. The speed is kind of slow, 1/10 the speed of light. Compared to these two, this is the slowest. Okay, then let's look at the next column. The next column is beta. Beta is actually electrons. Okay, electrons. So electrons with high speed. Electron which move at high speed, and that is beta. The charge is -1. As you can see, electron is -1. It's small, so to stop it, we can't use a piece of paper. It can penetrate through the paper, so we need to use something which is denser. So aluminium, so stop by aluminium, and very deflected. Very deflected compared to alpha, right? Alpha deflected only without the words very, because this is heavier. Beta is electron, which is lighter. So lighter, you want it to deflect, it's easier. So that's why they put here very deflected. You put this in electric field, it will deflect quickly to the positive terminal, as it is light. So ionizing effect is weak. Okay, it's weak. Of course, ionizing effect is strong or weak, and depends on the charge. This is 2+. The charge is greater, so ionizing effect is stronger. This one, the charge is -1. Okay, so not as big as 2. So because of that, the ionizing effect is weak. The other thing is electron move very fast. They can't stop there and ionizing the air molecules slowly. So they will move very fast, and that's why the ionizing effect is weak. This is moving slowly compared to this. You see the speed. And this is 9 times the speed of this one. So this is slower. So it will slowly interact with the air molecule and ionize them. Okay. Now let's see gamma. Gamma is not a particles. Gamma is energy, electromagnetic radiations. Okay. So no charge, only reduced by lead. That means a piece of lead will stop part of the gamma radiation, not all of the gamma radiation. Will stop part of them.
So gamma is like UV light.
Yes, it's like UV light. UV light is electromagnetic radiation. So it's that kind of properties. It's like UV light through, like sunlight, like UV light, like X-ray, something that is energy. Okay, so it's wave. Okay, if you learn it in wave, you should remember gamma also, one of the members. Then not deflected by electric field, not deflected by magnetic field, because it has no charge. No charge, that it is neutral. Okay, so ionizing effect is very weak. Very weak because it has no charge, and very weak because it moves very fast. So the speeds of light, 3 times 10 to the power 8. So that is fast for lead to ionize the air molecules. Okay, so let's see the other side. Radioactive decay. So decay means breakdown. Radioisotopes, for example, uraniums, or for example, carbon-14. So they are radioisotopes. They are unstable arrangements of neutrons and protons. Is altered to make a more stable arrangement. So they are trying to explain why radioactive decay happen, because it is not stable. So they need to release some things away, maybe too much energy, making it not stable. So they have to release energy. Or maybe there are too many electrons, then they release electron to make it stable. Or maybe there are too many neutrons or protons, then they release neutron, proton to make it stable. Okay, so that is the reasons why radioactive decay happened, just to become more stable at the end. So the parent nucleus becomes a daughter nucleus and a particle, which is the decay product. So the particles here can be alpha, beta, or gamma. And elements with a proton number 2 lower and nucleon number 4 lower and an alpha particle is made. Okay? You know alpha particles is 4,2He2 plus. So that means there are 2 protons here and 2 neutrons there. So that's why alpha particles is made of 2 proton and 2 neutron. And because of that, an element that release alpha particles, right? So you need to minus 4 to the nuclear number. That's why you see 226 become 222. Where is the 4 gone? Taken by the alpha particle, of course, which is this one, 4. Then the proton number decreases by 2, basically because it's taken by the alpha particles. So you have the minus 4 to the nuclear number, minus 2 to the proton number. Then because of the changes in proton number, right, it becomes a new element. From radium, it becomes radon. Okay, so in general, if you have a particle X with nuclear number A, proton number Z, so after alpha decay, right? So the nuclear number have the minus by 4, then the proton number have the minus by 2, then it become a new element, and then 4,2 helium come out. Although I write 4,2 helium with 2 plus, but normally you don't see that in alpha particles. It's just fine, no problem. Okay, beta decay. So beta decay means release of beta particle, or which is electrons. A neutron changes into a proton. So that they give us a more detail here. The electron is not released straight away like that, It's actually a neutron. A neutron change into a proton plus electrons and an anti-neutrino. Okay, so this is something new, of course, so I have to explain that. But let's start from here first. Neutrons, no charge. Proton, positive one. Electrons, or beta, negative one. So it seems like from no charge, it become a positive charge and a negative charge, which at the end have no net charge also, Plus and minus cancel off. This one no charge also. So neutrons during beta decay, one of the neutrons in the nucleus will change into a proton plus a beta particles plus anti-neutrino. Okay. So anti-neutrino is what? It's just small particles, even smaller than electrons. So it just come out as a piece of things, So it has no charge. It has a very light mass. So and elements with the same nuclear number but with a proton number 1 higher. So we have to understand this also. Why the nuclear number is the same and why the proton number is 1 higher. So imagine you have X at the beginning and Z. So the A on top represents nuclear number. Nuclear number is proton plus neutron. Okay, so that's nuclear number. So what happened during beta decay is one of the neutron decreases, change into a proton. So neutron decreased by 1 unit, proton increased by 1 unit. That is what happens to element X over here. Okay, so what happened is proton plus neutron. Now you minus 1 proton, then you plus 1 neutron. Of course, you will get back the same answer. For example, if this is 52, this is 52, and then you minus 1 minus 1 neutron. Minus 1 neutron, minus 1 neutron, and increase 1 proton. So 52, you minus 1, then you plus 1. At the end, still 52. But the proton number from, let's say, from Z Now, because there is an increase of proton number by 1 unit, so it becomes Z plus 1 now. Z plus 1. Okay. So because of the change in the proton number, so it become a new element. Let's say I call it W now. From X, it become element W. It become a new element. And then beta particles, we represent it by using 0 and minus 1. Logically, this is reasonable because, left and right must balance, So left is just A, so right A plus 0. So it's fine. Left hand side is Z, so right hand side Z plus 1 minus 1. So it seems like it is balanced. Followed by the anti-neutrino. Anti-neutrino is like this. Okay, so anti-neutrino. Don't need to know more. Just remember it's 0, 0. And let's move on. Example, iodine 131. So if iodine 131, that means the nucleon number is 131. Proton number, you have to check periodic table, so 53. Yeah? Now it becomes xenon because 53 plus 1, 54. Xenon. Okay, so nucleon number remain, then beta particles, then the anti-neutrino come up. Anti-neutrino is just 0, 0. Okay, now we look at gamma emissions. Gamma emission by itself causes no change in mass number or atomic number. So that means no change in mass number, which is nucleon number, no change in atomic number, which is proton number. So there's no change in both. They just emit energy. So that means if you have X with AZ, now after gamma has been released from the radioactive decay, so the nucleon number remains, the proton number remains, or the mass number remains, the atomic number remains, so it is still the same element. The only difference is this one is high energy. So after releasing the gamma, so it becomes low energy. Some isotopes do not change in mass or atomic number. However, they emit energy as their particles rearrange themselves to become more stable. So they are trying to say that when they release energy, they are getting more stable. Okay, so that's the thing. Okay, so we have done radioactive decay. That means the alpha, beta, and the gamma. We have done that. So the next subtopic here is half-life. Half-life of a radioisotope. Half-life means half. That means 50%, right? Life of the radioisotopes. So it's the time taken for half the nuclei present in any given sample to decay. Okay, so nuclei, the nucleus of the atoms decay, break down. So for example, let's say the half-life is 2 hours for X. Let's say X is a radioisotopes. The half-life for X is 2 hours. So that means at the beginning you have, let's say you have 10 gram of X. Okay, then after 2 hours, half of the X, half of the nuclei of the X will decay. So that means 5 gram of X decay. 5 gram of X and decay. Okay, so now let's take a further look. After another 2 hours, so every 2 hours, half of the nuclei is going to decay. So which one should we look at? So of course it's the same. This is 5 gram. This is 5 gram. So it's just that this is decayed, this is undecayed. So if it's decayed, it becomes stable and nothing happened to them anymore. But for the one which is undecayed, haven't break down yet. So it will continue to break down. Half of this will break down. So half of that breakdown, half of 5 gram is 2.5. 2.5 gram of X decay and 2.5 gram remain as undecayed. So the 2.5 gram that decay add up with the 5 gram just now. So altogether we have 7.5 gram of X decay. So you need to know why it's 7.5 because 2.5 add up to the 5 gram from here. Okay, so let's take a further look. In another 2 hours, half of the undecayed nuclei is going to decay. Half of 2.5 is 1.25. So 1.25 decayed, and hence another 1.25 remain undecayed. So just now I said 1.25 decay. So add up with the previous one. So 7.5 plus 1.25, that should be 8.75 gram of X decay altogether. Okay, so that is the idea of half-life. Half-life will make the undecayed nuclei, will make half of the undecayed nuclei decay. Okay, so always look at the undecayed nuclei. So when you want to consider half-life. Okay, some nuclei are more stable than others.
So,
So, yes.
so basically, 10 divided by 2, we get 5 grams of undecayed X. And then 5 grams of undecayed X, divide 2, and I get 2.5 grams of undecayed X. So the
Yeah.
decayed one, I have to minus last, the 10 gram minus 2.5 gram of undecayed X. So I get 7.5 gram of decayed X.
Yes. So it's true. It's true to think in that way.
In half-life, what I will be getting through the calculation is the undecayed.
Yeah. And decay will become half and half again.
Okay, sir.
Yeah.
I understand.
Okay. So let's see one example. Okay. One example in past paper. So we have the half-life question here. So let's look at this. Oh, I think we can start from the beginning. So let's start from the beginning then. A sample contains atoms of a particular isotope of protactinium XYPA. Okay. A nucleus of this protactinium isotope contains 91 protons and 143 neutrons. State the value of X and Y in the symbol XYPA. Okay, so first we need to know X is the nuclear number. So nuclear number, we add proton and neutron. So 91 plus 143. So equal to 234. So equal to 234. So 234 is the answer. So which is the nuclear number. Now, why is the proton number? So we look at the number of proton, which is 91. So we write here 91. Okay, so that is how we answer the first part. Now we look at part 2. This isotope is radioactive. and it decays by emissions of beta particles, 0 minus 1 beta. Then after that, to an isotope of uranium, U. Complete the equations for the decay of a protactinium's nucleus. So as we can see here, nuclear number we have count 2, 3, 4. And then proton number we have count 91. Then after that, uranium increase the proton number by 1, become 92. Nuclear number remain the same because there is a decrease of neutron followed by an increase of proton. So 2, 3, 4 remain the same. Okay, so even if you can't remember that fact, decrease of neutron and increase of proton, it is still able to help by balance left and right. You see left hand side 2, 3, 4, right hand side is 0 plus something, right? Plus 2, 3, 4. So we can still balance it. So even this one, it helps also. Left hand side 91, right hand side 92 minus 1. So this is reasonable to take 92. Then we look at B. A radiation detector measures. Radiation detectors is basically the Geiger-Müller counter. So measures a background count rate in a laboratory of 32 counts per minute. So background count rate is due to the soil, due to the mountain, due to the rocks. So suggest two naturally occurring sources of background radiations. So you can see the rocks. You can see even the space. Okay, so if you want to understand more about rocks is basically maybe due to the earth, due to the ground, due to the building. You know, there are rocks inside the building and so on. Due to the stone, due to the minerals.
Actually, I don't understand what they are asking in B1. Can you like explain, please?
Background radiations, like what I mentioned, is the radiation from the natural sources, from the surrounding. Okay, from the surrounding. So
Oh, when a rock has energy like that.
yeah, so rocks have radioactive decay, and that's why it has reading. It has background radiations. Radioactive decay happens to rocks. Radioactive decay happens to space. So space example like the suns, like the stars, like the galaxies, like the cosmic rays. So they have radioactive decay happens there, and that's why it forms some background radiation, which means it forms some count rate from your Geiger-Müller counter. So remember that the count rate is not only from radioactive isotope, it's also from the natural surroundings. Okay, so now let's see this part. So on this side, the sample is placed in the laboratory close to the radiations detector, and the count rate increases to 544 counts per minute. So you have to know that this 544, right, has two parts. Okay, has two parts. The first part is the background reading, 32 counts per minute. So there's a 32 counts per minute. This is due to the background radiations. The radiations because of the rocks, because of the space. So the remaining 544 minus 32 is 512. The remaining is the radiations due to the sample. So the sample radiations. Okay, so these isotopes of protactinium has a half-life of 400 minutes. Predict a values for the count rates measured 1200 minutes later. So 1200 divided by 400 is equal to 3. So that means there are 3 half-life. There are 3 half-life. Okay, so in order to predict this, we have to start from 512. We start from 512 because 512 is the sample radiation. Don't care about the background. So 512 after 400 minutes, you divide by 2 for this value, it becomes 256. 256. After another 400 minutes, divide by 2, it becomes 128. After another 400 minutes, divide by 2, it becomes 64. Okay. Now this 64, you have to think about it. This 64 is the sample radiations after 1200 minutes. But don't forget that the background radiations is always there, the 32. So the background radiations. So because of that, the readings that you get from the counter, the Geiger-Müller counter, should be 32 plus 64, which is 96. Okay, so 96 count per minute. So that's the thing. The background is there. Be careful. Background. Yes.
Can I know where did you get 32 as background radiation and also 512?
Which is here. 32 is given here. The background reading, the background count rate. So it's here. And then the 512 is 544 minus 32 to get 512.
Actually, why did they put background radiation and sample radiation? What is the meaning actually?
Background radiations is due to the natural sources like rocks, like space. Sample radiation is due to these isotopes, protactinium. Protactinium. So that means you try to imagine you are here taking the Geiger-Müller counter to, normally we don't take, it's the machine that take it, so normally we don't take, but just for your imagination only, you are taking the Geiger-Müller counter. So the Geiger-Müller counter will detect the reading from the radioactive isotope, which is protactinium. Protactinium will supply 512 count per minute. But the problem is you are staying in the surrounding with rocks, with building, okay, with earth, the ground. They supply readings to the instrument also. The reading supply is 32 count per minute. So that's why the Geiger-Müller will detect 32 plus 512, which is 544 count per minute. So that's why it is this value. One is from the sample that you use, the radioactive isotope that you use. The second one is from the surroundings. So altogether you detect 544. And imagine after 1,200 minutes, this protactinium, right, has gone through 3 half-life. The radioactivity will decrease by half, decrease by half, and decrease by half for 3 times, and end up with 64. Okay, so now this becomes 64. The background reading is still there because the rock, the house, and the ground all give some background reading of 32, still 32. So that's why after 1,200 minutes, the reading is 32 plus 64, which is 96. So try to imagine it based on the pictures. Any question on it?
I don't understand why you took 512 and find its half-life to 64.
Yes.
So then.
Can you say again what are you trying to ask? Because I can't hear complete sentence.
Oh, actually, sir, why did you particularly choose to find the half-life of 500 and 512's the sample radiation?
Oh, because it's written here. The protactinium has a half-life of 400 minutes. It is protactinium, the sample, which have this half-life.
So
So that's why
the
we have to
background
use,
radiation is not the protactinium itself.
yeah.
Protactinium is like a mineral.
Protactinium is a radioisotopes.
Oh, radioisotope means, is it like a mineral also? A very reactive uh, mineral.
Yeah, radioactive mineral, fine. Yeah, to say that.
But it's not a mineral.
After all, this thing is come from the earth, so
Okay.
you get it from the earth. So it's generally known as mineral, like uranium, you call it mineral because it comes from the earth also, underground, you get it from underground. Yeah, so it's fine to say it as mineral.
So the background radiation is actually not from the protactinium itself.
Yes, not from the protactinium. It's from something else.
Yes, I understand.
Okay. Then, okay, so have to be very careful because the background reading is confusing us. Without the background reading, right, so everything should be very easy. Right? But with the background reading, then you have the minus, then after that you have to add back. That make us more confusing. Okay, so let's see part 3. Suggest one reasons why the count rates measured 1,200 minutes later may differ slightly from the value predicted in B part 2. So you predict to be 96, right? Maybe at the end of the day when you really use a Geiger-Müller counter to count, maybe you get 105, for example. So we have to give reason why in practical you may not get 96 exactly. So the reason is because random fluctuations. Random fluctuations meaning radioactive decay happen randomly. So this is theory. Theory is supposed to be 96, but in practical, maybe it doesn't really go to 96. It go around 96, basically because radioactive decay happens randomly. So that's the reason. Okay, so let's look at another question. Sometimes the question has no background reading and it becomes easier. Okay. Let's look at this. Like here, see, ignore background reading, ignore background radiation. Okay, that will be a good news. If you see ignore background radiations, that will be much easier. Okay, so let's look at this question from the beginning. Radon 220 is a radioactive isotope. The nuclide notations for radon 220 is 220, 86, Rn. Describe the composition of a neutral atoms of radon 220. That means you just look at this, right? And say that how many proton, how many neutron, and how many electron. So 86 is the proton number, so 86 protons. Since they say it's neutral, right? So they should have 86 electrons. The proton same with the electron. As this is positively charged, this is negatively charged. They cancel off to be neutral. And then to find the neutron, you minus 220 minus 86. So you get 100. 220 minus 86, you get 134 neutrons. Okay, so that is how you get 3 marks. So 1 marks for the protons, 1 marks for the electrons, 1 mark for the neutrons. Okay, then we look at B. A nucleus of radon 220 decay to an isotopes of polonium, which is this one. By emitting an alpha particles, complete the nuclide equations for the decay of radon 220. So you know alpha is 42. Then the nuclear number you have to minus by 4, become 216. And then the proton number you have to minus by 2 to get 84. A detector of radiation is placed near a sample of radon 220 and give a readings of 720 counts per second. The half-life of radon 220 is 55 seconds. Calculate the reading after 220 seconds. Ignore background radiation. So if you are going to ignore background radiation, you're not going to minus at the beginning, then after that you add back the background radiation. No need to do that steps. So you can straight away see how many half-life are there and keep divide by 2. So something like this. Our half-life is 55 seconds. So the total time taken is 220. So 220 over 55. Then we know that there are 4 half-life that happens to the radon 220. So it has initially 720 counts per second. Now we divide by 2 to get 360. This is the first 55 seconds. After another 55 seconds, you divide by 2 again to get 180. Then divide by 2 again to get 90. 1 half-life, 2 half-lives, 3, 1 more. After another 55 seconds, 45. So 45 counts per second. So you're not going to minus the background radiations at the beginning to get this, and you're not going to add background radiation to get the final. So we can avoid that 2 steps if you are allowed to ignore the background reading. So which is, I have to say that it's much more easier. Okay, so that's the thing. Now,
So,
let's see. Uh,
so basically to find how many half-life in order to get the answer, so we have to divide the nucleon number like 220 with the time, which is 55 seconds.
we don't take the number, we take the total time.
Oh, the total
The
time.
half-life.
Sorry, sorry, sir. Can you
We
repeat,
take the
please?
total time. Take the total time, divide by the half-life.
Okay, sir.
Right, to get how many half-life.
Okay, sir. So the half-life is 55 seconds.
Yes.
Okay.
Let's look at this side. Question 11. Bismuth 214 is radioactive. It has a half-life of 20 minutes. The nuclide notations for bismuth 214 is 21483Bi. State the compositions of the nucleus of bismuth 214. They want the nucleus. Compared to just now, is it? They want the compositions of the atom. Atom include electrons. Electrons is within the atom, but nucleus does not include electrons. Okay, so the nucleus has proton and neutrons only. So we just need to put, that's why I say 2 marks only. That's why we just need to put there are 83 protons based on the proton number given, 83 protons. And then the number of neutron is 214 minus 83. And then we get 131 neutrons. Okay, so that is what inside the nucleus. Now we look at part B. Bismuth 214 decays by beta decay to an isotopes of polonium. So you know beta is 0 minus 1. Then you have to know after beta decay, the proton number increased by 1 from 83 become 84 because the neutron changed into protons. Nucleon number remain the same because the decrease of neutrons that happens by 1 unit, right, is replaced by the formations of 1 proton. So decrease of protons is compensated by the protons. So that's why there is no change at the end. Then part C, the count rates for a sample of bismuth 214 is 360 counts per second. Predict the count rates from the sample after 60 seconds, after 60 minutes. After 60 minutes. So be careful with this 60 minutes. Okay. This is the total time given. Divide by the half-life, 20 minutes. So 60 minutes divided by 20 minutes is equal to 3. So that means there are 3 half-lives. So 3 half-lives. Initially, we have 360 counts per second. Now, they never mention any background radiation, so that's why we don't need to minus the background radiation and add back afterwards. So we can just straight away take the first half-life after 20 minutes. The 360 will become 180. After another 20 minutes, the 180 become 90. After another 20 minutes, the 90 become 45. So the final answer, 45 counts per second. So part B, stage 2 of the social, economic, or environmental issue involved in the storage of radioactive material with very long half-life. Very long half-life. So let's say certain radioactive material, their half-life are many, many years. So you need to store it. Of course, one of the problem is economical problem, high cost of storage, high cost of storage. So this is economical problem. When they say economic, that means talk about money lah. So we need more money to store it. We need more money to store it for a long time. And then environmental issue. Environmental issue, you may say they may have leakage into water supply. So the radioactive material may go into the water supply. So this is the environmental. So if you feel like, oh, I can't think of this, then you talk about social. Social, you can put this as the point. Causes cancer. Which is easier to think of. Radioactive material causes cancer. So it's a social problem. So that's how. Okay, now let's finish up the theory first. Before we do others, we have a bit more to finish. Okay, so we have done half-life. I think you get the idea already. Now let's see the safety precautions over here. Radioactive material is stored in a lead container and locked away. Pick up with tongs, not bare hands. So don't use hands to take the radioactive material. So you have to take it by using tongs. Okay, so tongs is just a holder, a long handle. Okay, so kept away from the body and not point at people. Radioactive material, right? So dangerous. Left out of its container for as short a time as possible. Okay, that means you have to go away from the container which store the radioactive material. Atomic model. Okay, this part is something basic. Atom consists of nucleus. The central part of atom make up protons that are positively charged and neutrons. Neutrons has no charge. These two types of particles are called nucleons. So whenever there's a nucleon, is actually protons and neutrons. They are bound together by the strong nuclear force. So the nuclear force bound the protons and the neutrons together. Electrons, almost massless particles which orbit nucleus in shells. So it's like the planets orbit around the sun. Is that kind of concept. Okay, so now let's see Rutherford's experiments. So Rutherford experiment is done in this particular way. They put a radioactive sample here. Then the alpha particles come out, and then it passes through a very thin gold foil. Then he realized that most of the alpha particles can move straight and reach the other end. and only very few of them change directions. So showing that the tin gold foil, right, is made of many atoms, but atoms are mostly empty space except the nucleus. So if the alpha particle collide, I mean hit on the nucleus, then it will U-turn. But if the alpha particle pass through the shell, so most probably it is not really affected. It will move in straight line. But if it knock sideways with the nucleus, then it will change direction a little bit. But the nucleus is so small, no? The nucleus is so small compared to the whole atom. Okay, so imagine how small is nucleus compared to the whole atom. Normally we say a football in the football field. So the football is the nucleus, and then the football field is the whole atom, which include the electron shell where electrons are orbit around it. So from there you can see why most of the alpha particles will move straight. Basically because many empty space in atoms. Okay, so that is all about the experiment. So now you see the word. Tin gold foil is bombarded with alpha particles. That means you use the alpha particle to pass through the tin gold foil. The alpha particles are positively charged. Most pass straight through. Okay, but few will repel so strongly that they will bounce back or deflected at large angle. Deflected at large angle is just very few. Why they bounce back? Because they're not on the nucleus, so they bounce back. So conclusions, Rutherford concluded that the atom must be largely empty space with its positive charge, and most of its mass concentrates in a tiny nucleus. So that's why they move straight. Okay, so that's the experiment that make us understand the structures of atom. So at the end, you see nucleus. The nucleus is composed of protons and neutrons. Proton number of proton in an atom. Nucleon number, the number of nucleons, which is proton plus neutron in an atom. Now you see isotopes. Isotopes, atoms of the same element. That means they have the same proton number that have different number of neutrons. So example, carbon 12. Carbon 12 is 12, 6. Carbon 14 is 14, 6. So from here, 6 proton, 6 neutron, 6 electrons. For this, 6 proton, because of the proton number. Neutron, you take 14 minus 6, and you get 8. Electron, same with the proton, 6. So from here, you see isotopes have the same proton number, but different number of neutrons. There are non-radioactive isotopes and radioactive isotopes. So normally the one which is lighter is non-radioactive, and the one that is heavier, 14 is heavier, right? So the one that is heavier are radioisotopes. So radioisotope means it is not stable, it will break down. So radioisotopes are unstable atoms which break down giving radiation. So the radiation here is alpha, beta, and gamma. Medical use of the radiations. So we can use the radiations for cancer treatment. It causes cancer, you see. Radiation causes cancer. But at the meantime, the radiation is used to treat cancer. So through radiotherapy. Of course, radiotherapy is not good, They kill the good cell as well as the cancer cell. So the rays kill cancer cells using cobalt-60. Okay. It sounds good here. Kill cancer cells, but at the meantime, they kill the good cell also. They never mention that. Okay, so uh, second point, industrial use to check for leaks. So leaking happens at the water pipes, and then you put radioisotopes, or we call it tracers. You add it to the oil, to the gas, to the oil pipe, or to the gas pipe, at positions where leakage happens. Then the Geiger counter will shows a higher reading there. So the radioisotopes will just gather around the leakage route, the leakage area, and that's why the Geiger counter shows a higher reading. Archaeological use. Archaeology means the study of the history. So, for example, you want to see how long is the dinosaur bone found, and then you can check the carbon 14 in the bone. Then you use the half-life concept to predict how long has the dinosaur died. So that's why we can predict backwards. So we call this carbon dating. Okay, so we have finished out all the theory, and for past paper we have done quite many also. And let's see one more. Okay, now let's see this question. This question is uh, a little bit different because there's a graph. Okay, we start from the beginning. 12a. A radioactive nucleus decay by the emissions of a beta particle. State what a beta particle is and give its charge. So it's an electron, I know. It's an electron. So we have to say that out. So the beta particle is an electron. The charge is -1. Then you get 2 marks. So now we look at B. The graph in figure 12.1 shows how the count rates from a sample of a radioactive substance varies with time. Okay, so you see the count rate keep decreasing. And how we make use of this graph is actually we have to find out the half-life from the graph. Okay, so what to do is you see the initial count rate is 4,000. Then you just need to divide by 2, which is 2,000. So 2,000 is here. And then you bring it to the graph, bring it down. Then you get 8 days. So here to here is 8 days. So 8 days is the half-life. So if you want to double confirm on your answer, so what to do is you take another half-life to double confirm. So to take another half-life, so the half of 2,000 is 1,000. And you bring it here, bring it to the bottom. So you see that take another 8 days. Another 8 days. So from here, we confirm already. So the half-life is 8 days. Okay, so let's look at the right-hand side. Following an accident, the soil around a nuclear power station is contaminated by cesium-137, which is radioactive. Okay, then a sample of this soil containing cesium-137 has a count rate of 180 counts per minute. Cesium-137 has a half-life of 30 years and decays by beta emissions. And you see the half-life is quite long, 30 years. Okay, now let's see. Calculate the count rate from the cesium-137 in the sample after 60 years. So again, you can see this question has no background radiation. So if there's no background radiation, so it should be easier. Okay, so we just count like this. Initially, it has the count rates of 180 counts per minute. And how many half-life are there? So you take total time divided by half-life. So 60 over 30 equal to 2 half-life. Okay, so if there are 2 half-life, so what to do is you just need to take the count rate 180, and after half-life, the first half-life 30 years, become 90. After another 30 years, it become 45. So it should be 45 count per minute. Okay, so that's how we handle it. And now let's see the next questions. Suggest why people do not want to live near the power station even after it has closed. So of course, this is
gamma ray.
Gamma ray lah, true. Okay. So gamma ray, right? So that has they're scared maybe have gamma rays come out. Okay, so reasonable. They may have radiation from the factory. Okay. And not just scared about gamma ray, even beta or alpha be scared also. So we don't want that. Maybe we also scared there is a leakage to the surroundings, the leakage of the radioactive isotopes to the water supplies, for example. Okay, so you may also say affecting their health as leakage may happen into water supply. Radiation from the power station, you may say, which may cause cancer. Okay, so okay. Now let's see some multiple choice question. So multiple choice questions, or even this one is good to do also. You see writing one. Okay, let's see how to handle that. Okay. 2 radioactive sources are used by a teacher. One source emits only alpha particles and the other source emits only beta particles. Suggest how the sources can be identified. So there are many ways to identify it. You know, alpha particles you can block by a piece of paper, but beta cannot. Okay, so one of the way is you put a piece of paper between the source of radiations and the detector. Sample emits alpha particles only has no radiation reach to the detector. Okay, so this is one way. And if you feel like, oh, you can't think of this way, so you can also think of electric field. Electric field will be fine also. Let the radiations passes through electric field. Okay, so of course, let's say alpha particle deflected to negative terminal. Okay, now B. The teacher also has a source that emits gamma rays. State two ways in which gamma rays are different from alpha particles. So this will be easier. So there are so many ways to answer this. You can say gamma ray have no charge. You can say gamma ray have no mass. And so many other possible answers. Like for example, you can say gamma ray travel at the speeds of light. You can say gamma rays is a wave. You can say gamma has less ionizing power. Gamma ray has greater penetration power. Gamma ray is not deflected by electric or magnetic field. So many ways to put in this question. Now, there's just one tool, by the way. State an effect of ionizing radiations on living things. So ionizing radiation, that means you know alpha particles has a very strong ionizing power. So what is the effect? It may cause cell mutations. Okay. Cell mutation may happen, or maybe damage the cell. This is the easier words. If you don't want mutation, which is difficult to understand maybe, then you just write cell damage. Okay. Now let's see some multiple choice. There's a quick one, multiple choice. Okay. So like what I said, if the alpha, beta, and gamma entering magnetic field, you want to determine its direction, right? So basically you have to use Fleming left-hand rule. Fleming left-hand rule. So Fleming left-hand rule, you know, when you use Fleming left-hand rule, you have force
magnetic field and current.
Force, magnetic field, and current. So we talk about current first. If beta particles is moving to the right, then current is to the left. This is reasonable because you see in a circuit, right? So if there is a current moving from positive terminal to negative terminal, then electron is moving in the opposite direction. So if beta particle, which is electron, is moving to the right, current should be to the left. So when you use Fleming left-hand rule,
Current, I think the answers are C.
see,
Yeah.
down the page. Okay, so which is correct? And let's do one more, 37. Below are 4 statements about isotopes of a certain element. Which statement about the isotope must be correct? Isotopes, same number of protons. Same number of protons. Okay. So consider enough for this chapter.